Hello students. In our previous episode, we discussed mathematical induction and also worked out 3-4 problems. Now, you must have noticed that all those problems were from algebra. So don't think that it is only for algebra. Today, we take an example of geometry as well. You all know that in any polygon, sum of all the interior angles is n minus 2 times 180 degree. Now, this we can prove by mathematical induction. As you know, for any polygon, the number of sides n is at least 3, which makes it a triangle. And we know in a triangle, sum of the 3 angles is exactly 180 degree. Thus, P1 is true. Now, next we have to assume the result for k and then prove for k plus 1. For this, first we assume that result is true for k, which means that any polygon having k sides will have the angle sum k minus 2 times 180 degree. And from this assumption, we have to prove for k plus 1 sides. For this, we draw a polygon A1, A2, A3 and so on up to AK, then AK plus 1. So, before us we have a polygon having k plus 1 sides, namely A1, A2, A2, A3 and so on up to A3 up to AK, then AK plus 1 and AK plus 1 A1. Here the dotted lines indicate the missing sides, which cannot be shown in a diagram. In fact, this dotted line indicates the sides A3, A4, A4, A3 and so on up to AK minus 1 AK. Now, if we join AK with A1, we have two polygons, one with k sides, other with k plus 1 sides, namely A1, A2, A2, A3 and so on up to AK A1. This has k sides. And secondly, A1, A2, A2, A3 and so on up to AK A plus 1 and then AK plus 1 A1. Now, as seen in the diagram, clearly angle sum of the polygon A1, A2 and so on up to AK plus 1 equals angle sum for A1, A2 and so on up to AK plus angle sum for the triangle A1, AK, AK plus 1, which equals k minus 2 times 180 degree plus 180 degree, which equals k minus 1 180 degree, which further equals k plus 1 minus 2 180 degree. This implies Pk plus 1 is true. Thus, both the steps of induction are complete. So, we can claim that Pn is true for all n belonging to n, which means for any quadrilateral we can establish a well defined formula for the angle sum. Now, so far whatever problem we considered in which either equality was involved or inequality was involved, but in mathematics there are other problems in which there is no equality or inequality, but some other relation is mentioned, that x to n minus y to n is divisible by x plus y. First we check for P1. We have P1 equals x square minus y square divisible by x plus y, which is true because x square minus y square is always x plus y times x minus y, and clearly x plus y is a factor of x square minus y square. Our next step is to assume it for k and then try to prove for k plus 1. So, let us assume that p k be true. This means x 2k minus y 2k is divisible by x plus y. For p k plus 1, consider x 2k plus 1 minus y 2k plus 1. This equals x 2k plus 2 minus y 2k plus 2. Now, we can arrange this as 2k plus 2 minus y 2k plus 2, which can be arranged as x 2k plus 2 minus x square y 2k plus x square y 2k minus y 2k plus 2. Now, here in the first two terms x square is common, which gives x 2k minus y 2k. In the next two terms we have y 2k common, which gives x square minus y square. Now, clearly the first term is divisible by x plus y as per our induction assumption hypothesis, while the second term x square minus y square is obviously divisible by x plus y. In this manner, the entire right hand side is divisible by x plus y, and hence left hand side should be divisible by x plus y. That means x power 2k plus 2 minus y power 2k plus 2 is also divisible by x plus y, and thus we have proved p k plus 1 is also true. Thus, both the two steps are cleared. So, we can claim that P n is true for all n belonging to n. It means the given result is true for all natural numbers. We can take one more such example in which we have to discuss about the divisibility. Suppose we have to prove that 41 raised to power n minus 14 raised to power n is divisible by 27. As before, first we check the result for n equal to 1. So, P1 stands for 41 minus 14 is divisible by 27, which is true obviously, because the number itself is 27. So, P1 is clearly true. We have done the first step. Now, for the second step, we have to slightly play some trick. First, we assume that f k is 41 power k minus 14 power k. This implies f k plus 1 is equal to 41 raised to power k plus 1 minus 14 raised to power k plus 1. Now, from these two results, we eliminate 41 raised to power k term. So, we can multiply the first equation by 41 and subtract from the second. So, we get f k plus 1 minus 41 f k equal to minus 14 power k plus 1 plus 41 times 14 raised to power k, which equals 14 raised to power k times 41 minus 14, which equals 27 times 14 raised to power k. This means f k plus 1 equals 41 times f k plus 27 times 14 raised to power k. In right hand side, the first term is divisible by 27 by our induction hypothesis, while second term clearly has a factor of 27. So, it is divisible by 27. As a result, the entire right hand side is divisible by 27, which implies left hand side divisible by 27. That means f k plus 1 is divisible by 27. This means p k plus 1 is true. Hence, we can claim that by mathematical induction, P n is true for all n belonging to n. So, we have given two examples on divisibility using mathematical induction. Having done this, we would like to emphasize one point: why this kind of approach gives a guarantee that the result is true for all values of n. Actually, the name mathematical induction is misleading. It is not inductive process, it is actually a deductive process. In fact, when we first verify for 1, that is P 1 we verify, then we assume P k, and on the basis of that we prove P k plus 1. Now, how these two steps guarantees for all natural numbers, that is interesting to see. In fact, when we say P k implies P k plus 1, this k was not fixed, this k was arbitrary. Also, we have already shown P 1 is true. Now, the first step and second step are apparently infinite steps. How? When we apply 1 to second, we get P1 implies P2. This gives third. When we apply third to second again, we get P2 implies P3. We get fourth. When we apply fourth to again second, we get P3 implies P4. And this way we have no limit, we can keep on apply it. So that whole application is summarized in step 2, and hence it is true for all values of n. This is the logic behind induction. Well, so in this episode we have completed the idea of mathematical induction, taking almost all variety of problems to prove using mathematical induction, because we have covered almost all types of problems in our episode. Thank you very much.